Thank you very much, and I thank all for attending this lecture, or call it as you prefer. Well, I don't consider myself an expert in replications. So basically, what I'm trying to do in the last years is a bit try to sensitize to some topics, and specifically in this case, I'm going to talk about replications. What are replications? Why we need replication, and we also touch a bit about meta research and why I think we need meta research. I will show you who are the real experts in sports science in this moment in replication. And so if you want to know more, you can read our papers or the papers that are coming soon. So I start immediately with my presentation. Basically, in 2017, some authors published this manifesto for reproducible science. This happened after another important study was published a few years before, and basically these authors try to present the case for the poor reproducibility of research findings. So just to introduce briefly this topic, I just want to remind you the different stages of research. So when you start research, you need to generate some hypothesis. So you have a question that is translated in a research hypothesis. You design the study, you conduct the study, you analyze the data, you interpret the results, and in the end, you try to publish. Unfortunately, each of these steps may introduce bias. For example, even when you develop a specific hypothesis, you may fail to control for potential bias, including cognitive bias, and we see this later. When you design a study, you need to be sure that the study is involve enough participants to allow you to answer to your research question and to find if in a frequentist domain statistically significant results. You have to conduct the study, so the quality of the measurements can introduce some bias. And once you have the data and you start to analyze, this step can introduce a huge problem in our area, which is called p-hacking. So basically, when you don't declare in advance what kind of analysis you are going to run, you can change and try different approaches until you don't find something significant. And this is called p-hacking. And the same is for when you interpret the results, because, for example, you may focus on the few results that are statistically significant and ignore the one they are not. And the other problem is publication bias, because there is a trend to publish more positive studies than negative studies, and this depends on different factors. One factor is that the so-called drawer effect. You don't even submit a paper because the results are not significant, but if you submit it, you may find reviewers and editors that are not really open to publish negative studies. The reason why people, our peers, don't like negative studies, there are different reasons. One reason is, I don't know if I should say, but I do. Basically, journals are evaluated based on their impact factor. There is this idea that negative studies are not well cited. So some journals are resistant to negative studies because they think they decrease their impact factor. So now, as Job said, this is a sort of chat among friends and colleagues. So I may say something inconvenient, but This is actually one of the reasons why journals are not open to negative studies. And I had this experience discussion with other editors. So if other editors don't agree with me, I would be happy if they intervene publicly and say that they are open to negative studies. Personally, as a science and medicine journal, we are open to negative study. We don't care about the impact factor or anything. But this is not something so common, so you may find difficult to publish negative studies. And the p-hacking and publication bias, together with generic or not specified hypothesis, can generate another questionable research practice, which is called hacking. So hypothesizing after the results are known. So basically, you have the results and you create an ad hoc hypothesis or research question based on the results. Of course, all these steps make science less reproducible. And this is actually what these authors try to warn peers in this manifesto. So as I mentioned, this article was published after basically the first replication project was published. And this is a replication project from the Open Science collaboration that basically they try to replicate about 100 studies published in the three main psychological journals. And now I'm showing you the results of these studies. So first of all, what you can see here is these are the replication effect size, and these are the original effect size. This identity line is when the effect size of the replication correspond to the same effect size of the original study. So as you can see, there are a number of studies that are close to this line, but the majority are below this line, which means that in the replications, the effect size in general was lower or much lower. And this is a bit problematic. So this is another representation of the same results. So you can see here the mean effect size and the distribution of the original studies, the one that the authors try to replicate. And here you can see the effect size of the replications. As you can see, these effect size not only are lower, but there are also a lot of negative effects. So the effects was not similar or compatible with the original studies, but was in the opposite direction. And this is the other interesting finding is about the p-values, the famous p-values. So you can see here the p-values of the original studies. Consider that the authors replicated mostly statistically significant studies, and you can see here p-values. So the p-values, of course, the majority are below 0.05 because this is how they were selected. And these are the p-values of the replication. As you can see, not only the median replication is higher, but there are a lot of non-significant findings in the replication. So in other words, out of the 97% of the 100 studies that they replicated, they could obtain a significant finding in 37% of the replications. I will not enter too much into the details of how to evaluate whether a study replicated or not. There are different methods. So if you're interested, I invite you to read these studies, for example, in which they explain the methods they use. There are different ways to do that. So just take now just as a generic statement. So as I said, 37% of the replication could not find the same results as the original studies. The same approach, so the same replication, a similar project was conducted in other areas. So, for example, here again in psychology, with the many labs, the authors replicated previous studies, and their replication rate was a bit higher, a bit better, for 54%. And again, the original effect size that on average was 0.6 in the replication was much lower, so 0.15, which means from a moderate to large effect, they basically they found negligible or small effects. The same was replicated in social science. In this case, they found 62% of the studies could replicate the original studies, which is, I would say, maybe not ideal, but not bad. But the effect size, again, was 50% of the original, so was half of the original study. The same was done in economics. They could replicate 61%, and the effect size was 66% of the original. And finally, another study in preclinical cancer biology found 40% of the studies showing a significant result was replicated, and 80% of the studies showing negative results could be replicated. And the effect size was much smaller than the original, was 85% smaller than the original. So as you can see, the replication rate ranged from 30 and something percent to about 60%. So basically, this is one of the reasons, this study is one of the reasons why people start to mention about the replication crisis. I just want to remind you that when you replicate a study, you don't expect it to replicate completely the original findings. So if you have 50% of positive findings, you don't expect to replicate 50% of positive findings, but still, if the replication are properly done, so with the appropriate power, you expect at least to have findings that are compatible with the original effects. So now you may wonder, what about sports science? Well, let's dig a bit more in this area. So in sports science, some authors raise the issue of replication. So basically, as I show in the manifesto, there are critical issues in when conducting research that can increase the poor replication, or that can decrease the replication. And these authors start to examine some of these key issues to understand if we have a problem in that area, and if we have a problem, this may be may raise the suspect of suffering the same problem as in the other areas. So these authors mention a series of reasons why studies in sports science may be difficult to replicate. And among the reasons, there are the same that I show you in the manifesto. So arcing, questionable research practices in general, p-hacking, publication bias, and underpowered studies. So let's have a look to the first problems, let's say arcing, p-hacking, questionable research practices. Of course, we can't know exactly if these occur, but we can analyze the data, and we can try to estimate if we have this kind of problem. So this is how you have to interpret the next studies that I'm going to show you. So this is a study published on the British Journal of Medicine, in which the authors try to examine how many times studies support their hypothesis. And this was done in sport and exercise medicine. So what they found is that the 82% supported their hypothesis. And if we split in studies fully supporting or partially supporting the hypothesis, we basically have a 96%. So let's say that out of 10 studies, 9 studies confirm the hypothesis of the authors, which is a bit too much. If you think, I'm sure you agree with me, it's a bit too much. So there's something similar was done by other authors, and they published this article in the Journal of the STORC, the Society for Transparency, Openness, and Replication in Kinesiology, that I invite you to join and support. I'm biased. I'm a member of this society, but I think it's very important that we help each other. Anyway, what they found is that about 50%, close to 50%, fully supported their hypothesis, and other 30% partially supported. So as in sport medicine, more than 70%, 75% of the studies seems to support or partially support their hypothesis, which is again a lot. So either we are all genius and we can find the right design, the right question, so we are always right, or there's something weird there. Some other authors have run some more accurate analysis, and now I present an analysis of David Borg. David Borg now is working for the Australian Institute of Sport, and basically what they show, if you look at the distribution of the p-values according transforming z values here and here, you can see that in close to the statistically significant limits, there is a jump in the number of studies that show a significant results. So let's say in this area is not significant, in this area is significant. As you can see, corresponding to this threshold, there is a jump in the number of studies showing significant results. And again, this is a bit suspect. And the same is for the confidence intervals, and you can see this here. So in correspondence of 1, which is basically, let's say, the equivalent of the statistical significant difference, there is a clear jump. So this study basically suggests that the distribution of the p-values and the jump in the confidence intervals is not expected, at least. So there's something going on there. So if we consider these findings, that is, most of our hypotheses are confirmed, a jump in the distribution, an anomalous distribution of p-values and confidence intervals. We don't have a proof, of course, this is not evidence, but it's reasonable to suspect that we have a problem with p-hacking and hacking. In addition, in sports science, we have, in my opinion, a bigger problem than other areas, which is publication bias and underpowered studies. I combine both because now I show you why the combination of these two issues may introduce in our literature a lot of problems. So I just showed this editorial. So basically, Grant Abt checked the power and the number of participants in their studies, saying there, because Grant is an editor of Journal Sports Sciences. So they basically check in their publications the power and the number of participants. So what they found is that the median sample size is 19. If you think in terms of intervention studies, this means 9, 10 per groups. That if you have experience in sports science, you know it's a quite typical sample size, 10, 12 per groups. And what was a bit more problematic is that not only the sample size is very small, but only 10% presented an a priori sample size calculation, and none of the studies provided all the parameters to check, either to reproduce the sample size calculation or to check whether it is right or wrong. What I can say, having experienced the same problems in our journal, is that even when they provide all the information, which is unfortunately rare, what is not done is a justification of the smallest effect of interest. I'm not spending too much time today about that, but every time you use a large effect size in your calculations, you should justify why effects that are lower than large are not of interest for you, especially in sport, where if you speak with a coach or even with the researchers, they tend to tell you that any change can be relevant because it can make a difference between winning or losing, all these kind of things, which is a bit of a contradiction, because on one side we are interested in small effects, on the other we have studies that are powered just to find large or extremely large effects. So I come back to this study, because in this study is a narrative review, but they also provided the results of some simulations they made, and I'm using their simulation and their results because they are useful to make a point. So these are simulated effects of let's say hypothetical 1,000 studies. So what you can see here, these are three sets of simulated data. So here is simulated based on a sample size of 10. This is based on a sample size of 30, and this is 60, assuming an effect size of 0.5 as true effect size. The advantage of the simulation is that we can, normally we don't know what is the true effect size. In a simulation, you can set the true effect size so you can understand a bit more the distribution of the results in relation to the true effect size, because the true effect size is simulated. So in this case, it's 0.5. What you can see here is that the different sample size in the studies correspond to more or less variable effects coming from a replication of these studies. So, sorry. Yeah. So what I'm going to show now is what this means when we run statistical tests on these studies, and I'm referring to the condition with a small sample. So this is these are simulations of the effects of study using 10 as sample size. So what you can see here is that in this case, when the results, the findings are statistically significant, you have a very large effect size. In this case, it's 1.34. Remember that the true effect size is, because it's a simulation, 0.5. So when it's significant, the effect size is very large, 1.34 is more than the double than the original one. When it's not significant, the effect size is closer to the true effect size. Why this is important? Because if you consider, this is for the confidence intervals, you have the same problem. Confidence intervals with a small sample are are wider than with a bigger sample, but this is something you know very well. So what I was saying is that what happens when you use more sample is that in a situation in which we have 60 participants, and this is the effect, if you replicate 1,000 times, all the replication, of course, distribute very close or closer to the real effect. So for effect higher as 1 or more, you don't have, or you have a very small chance to have a study with an effect that is higher in this case than 1. If you reduce your sample to 30, so the power in this case is 48%, you start to see that in the simulation, you have some studies, a simulated study that can produce effects that are higher than 1. When you look at the very small sample, so with 10, you see there is a very high proportion of studies with effects above 1, and the same on the other tail. So what's the problem here? The problem is that these extreme are the one that result statistically significant. So when you publish a paper on, when people select a paper to publish using a small sample size and significant results, they tend to publish exaggerated effects. And when you combine this with publication bias and p-hacking, this is what can reduce the replicability of the findings. In other words, small samples produce effects that are more variable. And the extreme, the highest effects are also the ones that are statistically significant. So if authors tend to publish only statistically significant results, given the publication bias, drawer effect, and so on, or if the authors play a bit with the data in order to find something significant, as you can imagine, when you try to replicate these studies, it's much less likely that you can replicate the same effect, or you can obtain an effect which is compatible with the original effects. And this can decrease the replicability of the findings. So this is unfortunately the elephant in the room, meaning that normally the studies in our area have 10 plus 10 participants. Can be sometimes even lower, 8, or sometimes slightly higher, 12, 14, something like that. But we are always around that number. Well, with that number, the power is very low. So we are talking about less than 20% if you want to detect a moderate effect. But even if you want to detect a large effect, is about 40%. So half of the target power that normally we want for a study, which is 80%. And this is the situation is not much better if we want to detect a large effect size. In theory, we need about 60 per group. Okay, you can use some strategy, adding covariates, confounders to improve the power, but from 60 per group, you don't go back to 10. So you can reduce to 50 maybe, but these are the numbers that normally we would need to detect a large or a moderate effect size. 64 is for a moderate effect size, not even not a large effect size. For a small effect size, I don't even consider, because it's basically not. It's almost impossible to do it because you need hundreds in each group. But even if we stay around a moderate effect, in theory, in our study, we should have more than 50 per group as a minimum. Even using a large effect, which is actually something we normally do, we would need for a large effect 26 per group. Again, with some trick, you can have 20 per group. So our normal sample, as shown by Grant, so the magic number close to 10, is almost always not adequate unless we have a good reason to assume or hypothesize that very large effects are the only effect of interest. But this is quite unreasonable. When I say very large, is that with 10 and 10, basically you have a power of 0.8 to detect effects that are about 1.3, 1.5, or even higher, which are extremely large. Again, when you use an effect for your sample size calculation, you should explain why. And when you are targeting a large effect, what you are saying implicitly is that lower effects, so moderate effects or small effects, are not relevant and not practically relevant. And this is, I'm happy after to discuss with you, this is unreasonable. There are very few situations in which a large or very large effect can be justified, and even in that situation, even if a large effect is expected or can be justified, the relevance of the study themselves may be questionable. So, like it or not, our 10 plus 10, 12, 12, whatever you want to use, are always underpowered. So, what about sports science? Well, in sports science, luckily, we have 4 crazy researchers that years ago decided to replicate the same projects that similar to the one I showed you at the beginning in psychology, social science, cancer, and so on, in sport. And they did a great job. I say they are crazy because this is a massive job. And for me, these are the fantastic 4, because either you are a superhero or you are crazy to do something like that. Maybe they are crazy, but I don't know. let's say they are superheroes. And they try to do the same. It's a very complicated study, and they have just recently published some results. So they have replicated 25 studies. I think the study is going on, so it's possible that in the future there will be more. But out of these 25 studies, they could replicate 28% only of the results. So now I just show you some issues we have, some results from studies from meta research suggesting there's something weird in our studies, and it seems that their replication rate reflect the doubts coming from the studies that I just showed you. If you want to read the paper, you can go to OSF. This is where they have uploaded the manuscript that I think has been accepted or close to be published in a journal, and where you can find more details. I just show you quickly a couple of features that are interesting. So here you can see these are in orange the original studies, and in blue the replications. What you can see here immediately is that there's the replication have a much lower effect than the original one. Where you see this symbol, these are all the studies that are not where the effect is not compatible with the original one. Sorry. Okay, so here you can see, for example, in this these are this is partial eta square, and this is Cohen's d. This is completely much lower. So here is about 1 while the replication is closer to 0.3. If you look at the partial eta square here, you can see the original one and the replication. So that is almost excluding basically one case, the results are always much lower, and a higher proportion of results where you see the symbols here, the effect is not compatible with the original one. You can read in the paper what it means compatibility, but at the moment, just take it as I'm communicating the results. They are not compatible with the effect. And in general, they found that the replication have a 75% lower effect than the original ones. Again, if you think about the problems we have in our literature, so a lot of confirm hypothesis, jumping the p-values when you look at the distribution, this seems to confirm that we have some problem in our area. So as I told you, this is these are the stages of research, and as we have seen, there are a lot of areas in which the researchers can make decisions. The problem is that if these decisions are not planned and are not declared in advance, and we give researchers the freedom to play a bit with the study and with these areas, this can produce false positive. And this introduce bias and therefore false positive. I show you quickly this study. In this study in psychology, the authors try to understand, again with simulations, the proportion of false positive discoveries when you allow to play with some researchers' degree of freedom. It's a bit clearer here. So basically, they had these 4 situations. One is the possibility to approach, to use dependent variables and to approach statistically in different ways. The other degree of freedom is the possibility, for example, to add participants when you don't find significant differences. So you collect the first 10, you don't, you say, okay, let's collect other 10, for example. Controlling, so adding factors, adding factors to the model. And another possibility is, let's say you have 3 conditions, you can drop or add a new condition. These are the 4 degrees of freedom that the authors allow to be manipulated in the simulation. And what you can see here is that each of these single factors produces some false positive. But when you allow to combine these factors, you can, let's focus on the p below 0.05, you can generate more than half, 60% of false positive. This has been also done in also in our areas, for example, for training load and other things. When you allow people to manipulate things, even 2, 3, for example, dichotomizing a continuous variable or categorizing, dichotomizing with the ability to choose the threshold, this can generate a lot of false positive. And this is basically p-hacking. And as I told you, and as we have seen, we have a lot of researchers' degrees of freedom. So as you can see here, we can manipulate in some ways each of these steps. We can arc the hypothesis, so we can come back and change the hypothesis, we can modify the design, and we can interpret in a different way, we can select the results to interpret. So there are a lot of areas that allow researchers to spin the results. So we need a systematic approach to identify these problems, because the noise generated by these questionable research practices is very high, which means we need a systematic way to understand the extent of this noise. And so the first step to find a solution to a problem is to identify the problem, which may seem obvious, but in reality is not that obvious, because a lot of discussions that we have, and I also have with colleagues, is exactly to identify or to agree about the problem, or even to agree that we have a problem. So the point is that only once we identify the problem, we can start to generate a possible solution. And this is the normal problem-solving process. So how do we identify the problem? Well, there is an area of investigation which is called meta-research that I think we need in our area. I anticipate that when I say that we need meta-research, I'm implicitly saying that we need good meta-research. Meta-research, as any research, can be done properly or in a bad way. So, of course, when I say we need meta-research, I mean that we need good meta-research. Meta-research, if you don't know, is the study of research itself. So, is the study of methods, reporting, reproducibility, and so on. So there are the different aspects of research are investigated. The reason why I think meta-research is important is not only to identify the problems for finding solutions, but is also as a sort of post-publication peer review. We have the peer review system that should prevent bad studies to be published, but we well know that that's not the case for different reasons. The peer review is a minimum requirements, but it doesn't ensure basically anything. So bad studies can be nowadays easily published. If it's rejected, you will always find another journal that can publish. So the peer review is not a quality check, and this means that since published studies are published and with even if they are of low quality, it's very important that the community, the research community, examine these studies after the publication. And meta-research is a systematic way to review post-publication research findings. So this is, in my opinion, the only way we have to identify the questionable research practices and the errors. Of course, when I say errors or questionable research practice, sometimes are involuntary. And not necessarily researchers do that on purpose. Sometimes they just try different ways to analyze the data. They are not doing that because they know they are in some ways cheating. It's because they think there is something there, and they may start to think that their analysis is not strong enough to detect differences, and so they try different approaches. And this is not voluntary cheating, is just more maybe too passionate or too biased towards their hypothesis. So the fact is that we all make mistakes. I did so many in my career, and I'm sure I will do much more in the future. But the only thing we can do is to try to understand what we did wrong and trying to do better and trying to improve. This is the way sports science can progress and can improve. let's see what are the problems we have. Let's find the solution. Let's try to fight the temptation to always tweet or make claims on social media to get visibility, some invitation to some conferences, because I think that over time we risk to lose credibility.